Dear students, welcome to Bmat Section 2 Chemistry Quantitative Chemistry. Here are the learning objectives. This lesson is quite long, so make sure to go over the full specification of learning objectives afterwards. Let us begin. Formula mass and the mole concept. To calculate the formula mass of a substance, the sum of the average atomic masses of all the atoms represented in the substance's formula is calculated. For covalent substances, the formula represents the numbers and types of atoms compassing a single molecule of the substance. Therefore, the formula mass may be correctly referred to as a molecular mass. Consider chloroform, CHCl3, the covalent compound once used as a surgical anesthetic, and now primarily used in the production of the anti-stick polymer, Teflon. The molecular formula of chloroform indicates that a single molecule contains one carbon atom, one hydrogen atom, and 3 chlorine atoms. The average molecular mass of a chloroform molecule is therefore equal to the sum of the average atomic masses of these atoms. Figure 3.2 outlines the calculations used to derive the molecular mass of chloroform, which is 119.37 amu. A mole is defined as the amount of substance containing the same number of discrete entities, such as atoms, molecules, and ions, as the number of atoms in a sample of pure 12C weighing exactly 12 grams. One Latin connotation for the word mole is large mass or bulk, which is consistent with its use as the name for this unit. The mole provides a link between an easily measured macroscopic property, bulk mass, and an extremely important fundamental property, number of atoms, molecules, and so forth. The number of entities compassing a mole has been experimentally determined to be 6.02214179 times 10 to the 23, a fundamental constant named Avogadro's number, Na, or the Avogadro constant in honor of Italian scientist Amedeo Avogadro. This constant is properly reported with an explicit unit of per mole, the conveniently rounded version being 6.022 times 10 to the 23 mole. The molar mass of an element, or compound, is the mass in grams of 1 mole of that substance, a property expressed in units of grams per mole, g-mole, see figure 3.5. Because the definitions of both the mole and the atomic mass unit are based on the same reference substance, 12C, the molar mass of any substance, is numerically equivalent to its atomic, or formula weight in amu. For the amu definition, a single 12C atom weighs 12 amu, its atomic mass is 12 amu. According to the definition of the mole, 12 grams of 12C contains 1 mole of 12C atoms, its molar mass is 12 grams mole. This relationship holds for all elements, since their atomic masses are measured relative to that of the amu reference substance, 12C. Extending this principle, the molar mass of a compound in grams is likewise numerically equivalent to its formula mass in amu. Deriving moles from grams for an element. According to nutritional guidelines from the U.S. Department of Agriculture, the estimated average requirement for dietary potassium is 4.7 grams. What is the estimated average requirement of potassium in mole solution? The mass of K is provided, and the corresponding amount of K in moles is requested. Referring to the periodic table, the atomic mass of K is 39.10 amu, and so its molar mass is 39.10 grams mole. The given mass of K, 4.7 grams, is a bit more than 1/10 the molar mass, 39.10 grams, so a reasonable ballpark estimate of the number of moles would be slightly greater than 0.1 moles. The molar amount of a substance may be calculated by dividing its mass, G, by its molar mass, G mole. The factor label method supports this mathematical approach since the unit G cancels, and the answer has units of mole. The calculated magnitude, 0.12 moles K, is consistent with our ballpark expectation, since it is a bit greater than 0.1 moles. Deriving number of atoms from mass for an element. Copper is commonly used to fabricate electrical wire, figure 3.8. How many copper atoms are in 5.00 grams of copper wire? The solution is, the number of copper atoms in the wire may be conveniently derived from its mass by a two-step computation. First calculating the molar amount of copper, and then using Avogadro's number, Na, to convert this molar amount to number of copper atoms. Considering that the provided sample mass, 5.00 grams, is a little less than 1/10 the mass of 1 mole of COPPER 64 grams, a reasonable estimate for the number of atoms in the sample would be on the order of 1/10 Na, or approximately 1022 copper atoms. Carrying out the two-step computation yields. The factor label method yields the desired cancellation of units, and the computed result is on the order of 1022 as expected. Determining empirical and molecular formulas. Percent composition. The elemental makeup of a compound defines its chemical identity, and chemical formulas are the most succinct way of representing this elemental makeup. When a compound's formula is unknown, measuring the mass of each of its constituent elements is often the first step in the process of determining the formula experimentally. The results of these measurements permit the calculation of the compound's percent composition, defined as the percentage by mass of each element in the compound. For example, consider a gaseous compound composed solely of carbon and hydrogen. The percent composition of this compound could be represented as follows. If analysis of a 10.0 gram sample of this gas showed it to contain 2.5 grams H and 7.5 grams C, the percent composition would be calculated to be 25% H and 75% C. As previously mentioned, the most common approach to determining a compound's chemical formula is to first measure the masses of its constituent elements. However, we must keep in mind that chemical formulas represent the relative numbers, not masses, of atoms in the substance. Therefore, any experimentally derived data involving mass must be used to derive the corresponding numbers of atoms in the compound. To accomplish this, we can use molar masses to convert the mass of each element to a number of moles. We then consider the moles of each element relative to each other, converting these numbers into a whole number ratio that can be used to derive the empirical formula of the substance. Consider a sample of compound determined to contain 1.71 grams C and 0.287 grams H. The corresponding numbers of atoms, in moles, are. Thus, we can accurately represent this compound with the formula C0.142H0.248. Of course, per accepted convention, formulas contain whole number subscripts, which can be achieved by dividing each subscript by the smaller subscript. Recall that subscripts of 1 are not written, but rather assumed if no other number is present. The empirical formula for this compound is thus CH2. This may or not be the compound's molecular formula as well, however, we would need additional information to make that determination, as discussed later in this section. Consider as another example a sample of compound determined to contain 5.31 grams Cl and 8.40 grams O. Following the same approach yields a tentative empirical formula of. In this case, dividing by the smallest subscript still leaves us with a decimal subscript in the empirical formula. To convert this into a whole number, we must multiply each of the subscripts by 2, retaining the same atom ratio and yielding Cl2O7 as the final empirical formula. In summary, empirical formulas are derived from experimentally measured element masses by 1. Deriving the number of moles of each element from its masses 2. Dividing each element's molar amount by the smallest molar amount to yield subscripts for a tentative empirical formula 3. Multiplying all coefficients by an integer, if necessary, to ensure that the smallest whole number ratio of subscripts is obtained. Derivation of molecular formulas. Recall that empirical formulas are symbols representing the relative numbers of a compound's elements. Determining the absolute numbers of atoms that compose a single molecule of a covalent compound requires knowledge of both its empirical formula and its molecular mass or molar mass. These quantities may be determined experimentally by various measurement techniques. Molecular mass, for example, is often derived from the mass spectrum of the compound. See discussion of this technique in the previous chapter on atoms and molecules. Molar mass can be measured by a number of experimental methods, many of which will be introduced in later chapters of this text. Molecular formulas are derived by comparing the compound's molecular, or molar mass to its empirical formula mass. As the name suggests, an empirical formula mass is the sum of the average atomic masses of all the atoms represented in an empirical formula. If we know the molecular, or molar, mass of a substance, we can divide this by the empirical formula mass, in order to identify the number of empirical formula units per molecule, which we designate as N. The molecular formula is then obtained by multiplying each subscript in the empirical formula by N, as shown by the generic empirical formula Axb. For example, consider a covalent compound whose empirical formula is determined to be CH2O. The empirical formula mass for this compound is approximately 30 Amu, the sum of 12 Amu for 1 C atom, 2 Amu for 2 H atoms, and 16 Amu for 1 O atom. If the compound's molecular mass is determined to be 180 Amu, this indicates that molecules of this compound contain 6 times the number of atoms represented in the empirical formula. Molecules of this compound are then represented by molecular formulas whose subscripts are 6 times greater than those in the empirical formula. Note that this same approach may be used when the molar mass, Gmol, instead of the molecular mass, Amu, is used. I in this case, we are merely considering 1 mole of empirical formula units in molecules, as opposed to single units in molecules. The relative amount of a given solution component is known as its concentration. Often, though not always, a solution contains one component with a concentration that is significantly greater than that of all other components. This component is called the solvent, and may be viewed as the medium in which the other components are dispersed or dissolved. Solutions in which water is the solvent are, of course, very common on our planet. A solution in which water is the solvent is called an aqueous solution. A solute is a component of a solution that is typically present at a much lower concentration than the solvent. Solute concentrations are often described with qualitative terms such as dilute, of relatively low concentration, and concentrated, of relatively high concentration. Concentrations may be quantitatively assessed using a wide variety of measurement units, each convenient for particular applications. Molarity, m, is a useful concentration unit for many applications in chemistry. Molarity is defined as the number of moles of solute in exactly 1 liter of the solution. A 355 ml soft drink sample contains 0.133 moles of sucrose, table sugar. What is the molar concentration of sucrose in the beverage? Since the molar amount of solute and the volume of solution are both given, the molarity can be calculated using the definition of molarity. For this definition, the solution volume must be converted from milliliter to liter. Ideal gas law is a relation between the pressure, volume, temperature, and number of moles of a gas, PV equals nRT, where P is the pressure of a gas, V is its volume, N is the number of moles of the gas, T is its temperature on the Kelvin scale, and R is a constant called the ideal gas constant or the universal gas constant. The units used to express pressure, volume, and temperature will determine the proper form of the gas constant as required by dimensional analysis, the most commonly encountered values being 0.08206 liter at mol-1 Kelvin-1 and 8.314 pol liter mol-1 Kelvin-1. Gases whose properties of P, V, and T are accurately described by the ideal gas law, or the other gas laws, are said to exhibit ideal behavior, or to approximate the traits of an ideal gas. Dilution is the process whereby the concentration of a solution is lessened by the addition of solvent. For example, we might say that a glass of iced tea becomes increasingly diluted as the ice melts. The water from the melting ice increases the volume of the solvent, water, and the overall volume of the solution, iced tea, thereby reducing the relative concentrations of the solutes that give the beverage its taste. A simple mathematical relationship can be used to relate the volumes and concentrations of a solution before and after the dilution process. According to the definition of molarity, the molar amount of solute in a solution is equal to the product of the solution's molarity and its volume in liters. N equals ml expressions like these may be written for a solution before and after it is diluted. N1 equals M1 1 liter. N2 equals M2L2, where the subscripts 1 and 2 refer to the solution before and after the dilution, respectively. Since the dilution process does not change the amount of solute in the solution, N1 equals N2. Thus, these two equations may be set equal to one another. M1 1 liter equals M2L2. This relation is commonly referred to as the dilution equation. Although we derive this equation using molarity as the unit of concentration and liters as the unit of volume, other units of concentration and volume may be used, so long as the units properly cancel per the factor label method. Reflecting this versatility, the dilution equation is often written in the more general form. C1V1 equals C2V2, where C and V are concentration and volume, respectively. Volume of a diluted solution. What volume of 0.12 mHbr can be prepared from 11 ml, 0.011 liter, of 0.45 mHbr? We are given the volume and concentration of the stock solution, V1 and C1, and the concentration of the resultant diluted solution, C2. We need to find the volume of the diluted solution, V2. We thus rearrange the dilution equation in order to isolate V2. Since the diluted concentration, 0.12 m, is slightly more than 1/4 the original concentration, 0.45 m, we would expect the volume of the diluted solution to be roughly 4 times the original concentration, or around 44 ml. Substituting the given values and solving for the unknown volume yields. The volume of the 0.12 m solution is 0.041 liters, 41 ml. The result is reasonable and compares well with our rough estimate. The mass percentage of a solution component is defined as the ratio of the component's mass to the solution's mass, expressed as a percentage. A 5.0 gram sample of spinal fluid contains 3.75 milligrams, 0.00375 grams, of glucose. What is the percent by mass of glucose in spinal fluid? The spinal fluid sample contains roughly 4 milligrams of glucose in 5,000 milligrams of fluid, so the mass fraction of glucose should be a bit less than 1 part in 1,000, or about 0.1%. Substituting the given masses into the equation defining mass percentage yields. The computed mass percentage agrees with our rough estimate, it's a bit less than 0.1%. Note that while any mass unit may be used to compute a mass percentage, milligrams, g, kilograms, ounces, and so on, the same unit must be used for both the solute and the solution, so that the mass units cancel, yielding a dimensionless ratio. In this case, we converted the units of solute in the numerator from milligrams to g, to match the units in the denominator. We could just as easily have converted the denominator from g to milligrams instead. As long as identical mass units are used for both solute and solution, the computed mass percentage will be correct. Thank you for staying tuned. The next video is on oxidation, reduction and redox.